Hello and welcome to part 3 of our salty lessons. We are looking at how to calculate the pH for these salt solutions because remember, our salts can be acidic or basic or neutral, but neutral is pH of 7. Okay, so we have a 3-step process that we need to follow. Step number 1 is to identify which part or which ion of our salt is acting as our weak acid or base. This is going to be the ion that came from the weak acid or base in the neutralization reaction because that's the only one that's going to be able to hydrolyze water. If the ion is acting as a weak acid, we're going to set up a Ka problem using our Rice table. We have to write out our hydrolysis reaction though for that Rice table. For the hydrolysis reaction with an acidic salt, the acidic salt came from the cation, and we're going to take that and react it with water. Since it is an acidic salts must form an acid. They have to form H3O+. And then the remainder will be a weak base, which will be the conjugate of our original acidic salt. If our ion is acting as a weak base, then we're using our Rice table and a Kb problem. Hydrolysis reaction that we need to write for our rice with that basic salt is going to have the anion, which is acting as that weak base. It's going to react with water to form OH-. We have to form OH- in solution because that's what bases do, and it is a basic salt. The leftover will be the weak acid, which is the conjugate acid of that basic salt. There is one thing to definitely look out for on these sorts of problems. Most of the time, we're actually only going to be given Ka values, but we might need a Kb value. Remember from part 1, we can always determine Kb if we have Ka because Kb times Ka is always equal to 1 times 10 to the negative 14 or Kw. So that's going to be step 1, basically figuring out what is our acidic or basic salt and doing that Rice table Ka or Kb expression. From that, we're going to end up finding the H3O+ concentration or OH- concentration, again depending if it's an acidic salt or a basic salt. Acidic salts is going to be our H3O+ concentration that we'll find, and a basic salt will find our OH- concentration. Once we have the concentration of H3O+ and OH-, we can solve for pH or POH by taking the negative log. Be careful when you have that OH- concentration. When you take the negative log, you'll find the POH. We're still going to have to go back and subtract that from 14 to get just the pH. So let's go through and look at a couple of examples on these types of problems. On number 1 here, we want to calculate the pH of our 0.1 molar ammonium chloride solution, and we're given the Ka value for our ammonium. Well, in these types of problems, our very first step is going to figure out what kind of salt do we have. Is it acidic or basic? I'm going to look at my salt. The NH4 must have come from NH3, and that's a weak base. The Cl- must have come from HCl. That's a strong acid. Well, it's always going to be the part from the weak that's going to give us our hydrolysis reaction. It's from strong stuff can not split up or hydrolyze our water. So we need to take the part of our salt that can hydrolyze our water. It's not the NH3, it's not the weak base, because the weak base isn't actually in our salt. It's the conjugate, it's that NH4+, that is going to hydrolyze water, and we need to use to write our reaction, our hydrolysis reaction. So we're always going to start with the salt part. So in this case, our ammonium cation that will hydrolyze water. Well, we need to react it with water to see that split happen. Since NH4 plus is acting as an acid here, our cations will act as an acid. We also know it's acting as an acid since we had a strong acid plus a weak base to form that salt. It's an acidic salt. Acidic salts must always form H3O plus. So our NH4 plus here acts as an acid, donating that hydrogen to the water to form H3O plus. Then we're going to have our leftover, which is our conjugate base, ammonia. Once we get to here, we're ready to fill out the rest of our rice table to go into our second step here, which is calculating the pH. So as we're filling out our rice table, we don't need our liquid water. It's a liquid. They're not included in equilibrium. Well, we had a 0.10 molar ammonium chloride solution, so we're starting with 0.10 molar ammonium. Before that hydrolyzation reaction, we do not have any H3O plus or ammonia. We're going to go through our change in terms of X. So we have minus X, plus X, plus X. That's going to give us our 0.10 minus X, X, and X. Well, this is an acidic salt, which also means we have to do a Ka problem. So let's write our Ka expression. Once we have that Ka expression written out, we can go ahead and substitute in our equilibrium concentrations, as well as our Ka value the problem gave us. So we have that x squared and minus x part. We can go ahead and assume that our x here is going to be negligible. We are able to do that because our Ka is so much smaller than 1. So again, x will be negligible here. So then we can go ahead and finish out our algebra to solve for x. When we multiply our Ka value times that 0.1, we'll find that our x squared is equal to 5.6 times 10 to the negative 11. We'll take the square root of both sides to find our x, which is 7.5 times 10 to the negative 6. Well, our x is also equal to our H3O plus concentration, as we can see in our rice table. Well, now our last step is to find that pH. pH is the negative log of H3O plus. So taking the negative log of our H3O plus, or that x value, gives us a pH of 5.13. And this makes sense. Remember, we have an acidic salt. Since it's an acid, our pH should in fact be less than 7. Alrighty, we have one more practice problem to look at. You're welcome to pause the video and give it a go if you're feeling comfortable, but if you'd like to see another example worked out, go ahead and continue on. So this time we're looking for the pH of a 0.30 molar sodium fluoride solution. Our first step is still to identify what kind of salt do we have. Is this acidic, basic, or neutral? So as we go through this, we find that our sodium's from sodium hydroxide, which is a strong base. There will be no hydrolysis there. But HF is from a weak acid, so yes, there will be hydrolysis from that F- ion. So that's what we need to focus on. We also know that this salt came from the product of a strong base and a weak acid, so it must be a basic salt. We then need to write our hydrolysis reaction to go into our rice table. That hydrolysis reaction is always going to start with that ion that will hydrolyze from the weak. This is from our weak acid, F-. It's going to hydrolyze. Hydrolyze means that it's going to react with water to split it up. We have to determine what products. Well, again, this is a basic salt. Things that are basic are always going to produce OH-. If we made OH-, our basic salt F- did in fact act as a base, accepting an H+ from that water. So we're going to be left with its conjugate HF as well. In our rice table, we don't care about water. We're starting with 0.3 molar sodium fluoride as our initial concentration. We're going to find those equilibrium concentrations in terms of X. From here, we're ready to move on to our next step, which is using our Ka or Kb to find our concentration. Well, this is a basic salt. Since this is a basic salt, we have to use our Kb expression to solve for OH minus concentration. But the issue here is the problem only gave us the Ka value. We're going to have to use that Ka value for HF to calculate our Kb. Remember that relationship? Kw equals Ka times Kb. So we can rearrange that to solve for Kb, giving us Kb equal to Kw divided by Ka. Kw is always 1 times 10 to the negative 14, and then we'll divide by that given Ka to give us our Kb value of 1.4 times 10 to the negative 11. Now we can go and substitute everything in that Kb equilibrium constant expression. Once again, here we can assume that our minus x is negligible. This is because our Kb value is so much less than 1. So then when we go and solve for x, we're going to take the square root of the product of 1.4 times 10 to the negative 11 times 0.3. Again, we need the square root of that to get our x value of 2.0 times 10 to the negative 6 molar. And our x value is equal to that OH minus concentration. We can also check out our x. X is less than 5% of what we're subtracting it from, that 0.30. So that's also going to confirm that it is in fact negligible. So back to finding our pH. X is our OH minus concentration. So when we go and take the negative log of that, it's going to give us our pOH. That'll give us a pOH of 5.69. We still need to find the pH. pH plus pOH always add up to 14, so let's just subtract out that pOH. Okay, so 14 minus that pOH gives us our pH of 8.31. We want to be sure that we're always thinking about our sig figs throughout all of this business as well. So if we take a look back at our sig figs, our initial concentration and our Ka value had 2 sig figs, giving us 2 sig figs in our Kb, 2 sig figs in our X, but 2 sig figs in our X means 2 sig figs in our pOH. That's a log number. Sig figs are just what comes after the decimal. So in our pH log number, again, 2 sig figs. Those are the 2 sig figs coming after the decimal. So there you have it, calculating pH of a salt solution, which is basically a Ka or Kb problem. We just have to do a little bit more work to figure out what reaction is happening in that rice table. We'll have some more practice on this in class as well. Enjoy the rest of your day.